Okay, so I thank the organizers, well, some of the organizers for inviting me. So I'm embarrassed to give this talk at 2 levels. Well, first of all, I've given, some of you have heard a version of this talk, and the other is that what I'm going to tell you will mostly be trivial things, but I want to emphasize that, we can calculate some things in steady state almost trivially, but that gives us hope to calculate some things out of equilibrium. So if you think this is trivial, I would be interested to know how you would do things if we could do them out of equilibrium. So that's the kind of motivation. So I'm going to consider a disordered long-range exclusion process So unlike Stefano, my native language goes from left to right, so my particles will move from left to right. So it's again an exclusion process in a one-dimensional lattice. This is not an infinite lattice, so there are n sides. Can you guys over there see me? See this? Okay. So this is n sides. There's exclusion, of course. So let me give you with examples how the dynamics works. So each side either has a particle or not. Okay, so I have, I'll mark the bonds, so the edges between two sides. So I'll give them labels, B1, B2, etc. And particles enter from the left with rate alpha 0. So this is a continuous time process. So particles will enter from the left with alpha 0. They will keep going left until they find the first occupied site. So this particle, when a particle tries to jump in, this is occupied, this is occupied, this is occupied, so it will go and sit over there. Okay? So no matter where it sits, the entrance is right alpha 0. So that corresponds to the first bond that it crosses is B0. So that's the idea. This guy will hop with rate alpha 1. This guy will hop with rate alpha 2. This will hop with rate alpha 3. So all these will hit the same target site. Yes. So this guy, when it tries to hop, it will look at the first available site to its right, and it will go and sit over there. Similarly, okay, so maybe this is, I don't know, alpha 6. On the right, particles will escape also in the same fashion. So this guy tries to hop. It sees the next empty site, and so it'll just exit the system. So this is alpha 8, and then this is alpha 9. Okay. So is the model clear? So every particle tries to find the first available site to its right. So there's both exclusion and bond disorder. The alpha i's are arbitrary. They're not. They don't even have to be chosen from any distribution. You can, but you don't have to.
So the alphas are attached to the site, or is just how many particles
are attached to the site or the bond, if you like. So yes, irrespective of how many sites there are in front, this guy will hop with this rate. Yeah. So I'm going to talk about large deviations for the current, and immediately you can see that the current is alpha naught. So the current of particles across any given bond is clearly alpha naught, because if I look at this bond, the current is the same because of particle conservation, and I look at the leftmost bond, the current, I mean, this is Poissonian, so everything is kind of easy. So the current is clearly alpha naught. So, okay, so let me tell you some results about this process. Yes? Yes, totally asymmetric, yes, yes. Yeah?
Particles are sitting at very slow rate.
For me, alpha i's are arbitrary. I mean, I'm not going to give any values to them right now. What do you mean?
Suppose the last exit.
So, you mean which one? Alpha 9?
Yeah, alpha n.
Alpha n? Well, it doesn't matter, right? Because particles can. So, in particular, if all particles are, all sites are occupied and a particle wants to jump, it will just zoom through the system and exit. So, nothing will change. Okay, so I'll denote my configurations by W, which will be binary words of length n. So 1 corresponds to occupation and 0 corresponds to vacancy. So the generator of this process, MW prime, maybe I'll write it in the next. So I'll use physics notation. These will be column stochastic matrices. Mn. This is the probability to go from omega prime to omega if omega is not equal to omega, or W is not equal to W prime, and this will be minus sum over all, let's say V, probability V goes to W if W equals to W. Okay, so this is my generator, and I'll give an example in a second. So the first result, which is kind of easy, is that the stationary distribution it's not immediate maybe from the dynamics, is a product measure with density at site j rho j given by alpha naught plus alpha j. Okay, so somehow the entrance controls the entrance rate controls the dynamics. Okay. So this is the first result, but in addition, this model satisfies very nice properties, which I want to share with you. So this is the following is not an easy theorem. At least we don't know any easy proof. So this is myself, Anna Schilling, then Steinberg, and Nicolas Thierry. So if I look at the matrix Mn, its spectrum is very explicitly described. So the eigenvalues of Mn are as follows. So let S be a subset of 1 to n. Okay, and let alpha sub s be the sum over all I in S alpha I. Okay, so I just add the corresponding alpha i's. Then for every S which is non-empty, there is an eigenvalue given by minus alpha naught minus alpha s. Okay, so in particular, all the eigenvalues are linear in the parameters alpha I. So I'm not. So everything is in full generality. I mean, I'm not going to choose anything about the alpha i's. Okay, so let me give you an example. So let's take n equals 2. So M2, and I'll order my bases in Lex order. So I should give some space. So for later purposes, I'll leave some space. Okay, so for example, 0, 1 goes to 0, 0 with rate alpha 2, and I don't know, 1, 1 goes to 0, 1 with rate alpha 1, because if the first particle hops out, it'll jump out of the system. So that's this. Yeah? So this has eigenvalues. Well, 0 is an eigenvalue, of course, by construction. And so the other eigenvalues are minus alpha naught minus alpha 1, minus alpha naught minus alpha 2, minus alpha naught minus alpha 1 minus alpha 2. So it's very explicit. And this, it's kind of clear that all eigenvalues come because the number of subsets of an n set is 2 to the n. I'm excluding the empty set and I'm adding 0. Yes? So, but I mean, although the eigenvalues are so explicit, I mean, we don't have any simple proof of this. I mean, so to actually prove this result, we had to go to representation theory, and not even representation theory of groups. We had to do something more general, which was the representation theory of monoids. And in particular, even though the eigenvalues are so explicit, the eigenvectors are quite complicated. So that's, yeah, so that's the story. So, all right, so maybe let me just mention some history. So this long-range exclusion process was introduced by Spitzer, Frank Spitzer, in the celebrated paper on exclusion processes in 1970. And so he had conjectured that this process is well defined on ZD. Well, he had something more general, not this process here. And Liggett proved the existence of this process of this LREP in 1980 on ZD. So there it was more general. So so you consider a point configuration in ZD, on ZD, and what you do is when a particle tries to hop, you run some Markov chain on the state space, and you follow that trajectory of the Markov chain, follow that realization. The moment you find an empty spot, you go there. So it's much more general. So this guy can be thought of as a kind of trivial limit, where the Markov chain is deterministic. It just goes right. It just doesn't do anything else. So, but still, I think this is quite interesting, and yeah, I'll show you some other properties. Sorry? I have not seen it, no. I mean, it's not as nice. I played around with it, but it's not as nice. Yeah. Okay. So, all right. So let me go here. Okay, so now let me talk about current. So as I said, the current is given by alpha naught. So there's nothing particularly interesting going on here. So now we want to consider currents across individual bonds. So suppose I sit and measure the current across each of these bonds, okay, simultaneously. So I consider the joint distribution of currents. So want to measure the joint distribution of currents across B0, B1, so on up to Bn simultaneously, yes? And so the way to do this, wanted to keep this formula because Stefano very nicely, I'm going to use this formula in a second, but okay. Okay, so the way to do this is to introduce a tilted generator. So let lambda naught up to lambda n be the parameters well, conjugate to the current in a sense. I want to say involved in jumps across B0 up to Bn. So what you want, and Ln be the tilted generator. This is, of course, standard knowledge to the experts. So what I'm going to do is I'm going to multiply each transition. So every time a particle hops across a certain bond, I'm going to place e to the lambda I across bond Bi. I'm going to place e to the lambda I on that transition. So there's an e to the lambda 2 over here because this corresponds to this last particle exiting. This has e to the lambda 0. This has e to the lambda 1. This guy, okay, so let's look at this configuration. So, right. So this alpha naught corresponds to a particle entering into this configuration, right? So this, okay, so I've done some mistake. Yeah, so this should be e to the lambda 0 plus lambda 1. Okay, so when a particle enters here, it crosses two bonds. So I keep track of all of them. So this is e to the lambda 0 plus lambda 1. Similarly, for this guy, yeah, so this particle hops out, so it crosses both bonds B1 and B2, so this is e to the lambda 1 plus lambda 2, this is e to the lambda 2, and here, this is crucial, there is a possibility in this configuration for a particle to enter from the left, jump over everybody, and exit to the right. Yes, that's possible. So I have to add and subtract alpha naught times e to the lambda naught plus lambda 1 plus lambda 2 minus 1. Right? So this minus alpha naught corresponds to just the self loop, and this part corresponds to counting the current. Yes, is that clear? So I'm looking at the simultaneous, I want to calculate the simultaneous currents across each bond, but this is kind of, at the level of the stationary distribution, this is kind of trivial, because all of these currents are forced to be equal in stationarity. So this comes out from the calculation. So okay, so let me just say what this means. So let Q0t up to Qnt be the time integrated currents. Up to time t. Then the probability that Q0 t over t is little j0 and so on. Qn of t over t is little jn as t goes to infinity is, well, it will be the product of these delta functions j0 minus ji, I equals 1 to n, times e to the minus t times the large deviation function of j0, where f of j is the Legendre transform of mu of lambda naught up to lambda n, which this is the so this is my L2, sorry. This is the largest eigenvalue of Ln. Right? So this is the standard folklore for large deviations. Yes.
Where do your lambda 0 up to lambda n come from? They are parameters?
Yes.
But there were never lambdas before, so what are they?
No, they're conjugate to the currents in a sense. So, this is the variable that keeps track of the current across the bond. Lambda I is the variable that keeps track of the current. So when you calculate the largest eigenvalue of this will be the joint cumulant generating function for the currents, and its Legendre transform is the large deviation. So that's the standard. So as you can expect, maybe all of you have seen this already. So this is the theorem. Well, it's kind of evident. So this is alpha e to the lambda naught plus up to lambda n minus 1. And the large deviation function f of j is something that Stefano already wrote in the previous talk. J log j by alpha naught, with where his formula corresponds to alpha naught equals 1. Okay, which I can set without loss of generality by rescaling time. So, so the fact that the large deviation, so I should have said mu n is also the cumulant. So this is also joint cumulant generating function. Because we are in steady state, the cumulant generating function will only depend on lambda naught plus lambda. And I mean, this is all standard. I'm just saying trivial things, and I apologize for that. But
mu is n variable, right?
yes, mu. Sorry?
No, there are n variables.
That's right. That's right.
Because the Legendre transform also is n variable.
Yeah, but the delta function have.
So it's all the variables.
Yeah, has the same. Yeah. Right. So here there are n variables. You see. Yeah. Because we are talking in steady state, all the currents we know have to be the same. So, yeah. So, but here's something nice that really happens. Something really nice that happens. So, okay, maybe I'll write it on the next. So if I look at the eigenvalues of Ln, they're also given by the same kind of formula as before. In fact, except for the eigenvalue yeah, just let me finish. Except for the eigenvalue 0 of Mn, all other eigenvalues of Ln are the same as those of Mn. Okay, so this, just a moment. So this putting in all this humongous number of factors and doesn't change anything for all other eigenvalues. It just changes the first eigenvalue and that too by this. Okay? Yes, sorry, Ravish. Yes. Yes, in the long time limit, yes.
Yeah, in the long term. I want to compute the lambdas before we do this.
No. Lambdas are parameters, they are arbitrary. I mean, we want things as functions of, I mean, think of lambdas as the parameters in your cumulant generating function.
Correct, but I want it to match to this particular J0 to Jn.
Yes. No. I'm just explaining the relationship between this matrix and the large deviation function. So look at this matrix, calculate its largest eigenvalue. By Perron-Frobenius we know it's unique. So here it is. This is the cumulant generating function of the currents. This is, I don't know, Gartner, is this the same as Gartner-Ellis? Yes, that will happen. Yes, that's right. Yeah. I'm saying that will happen essentially because of conservation of particles. Because the currents, in steady state, the current across any bond is the same. This is just a property of conservation of particles.
Can you say something nice about the eigenvector corresponding to Benjamin's eigenvalue?
Yes. Both the left and the right eigenvalues are explicit. So I'm going to just say that. I'm running out of time. Okay, so let me just quickly say. So we can construct the quasi-stationary process. So suppose we observe atypical currents J0 up to Jn. Over a long time, then the corresponding quasi-stationary process for those values of the atypical current are given by the modified Doob transform, which Shetrit and Touchet have introduced. Sorry. Yes, I was going to say that. Yes. So these atypical currents for the quasi-stationary process again will satisfy the same constraint, which will be forced to be equal. In quasi-stationarity. Then the condition, the generator for the condition process, for the quasi-stationary process, let me just write QS, is the same, let's say Mn prime, is the same as Mn with alpha naught replaced by alpha naught e to the lambda naught plus up to lambda, which I can call alpha naught prime. So if I look at the quasi-stationary process, it has exactly the same properties as the original process. In particular, the stationary distribution for that process is a product measure with densities given by this, where alpha naught prime plays exactly the same role as alpha naught. And so that's also a nice property that pops out from this dynamics. Okay. Yeah, essentially. Right, exactly. So, okay, so I'm not going into too much detail here. Let me mention some generalizations of this. So this is what we called a Nonabelian Saridpite model. This is with the same authors that I mentioned earlier. So now you consider a tree. So you take a directed tree. So let me give you an example so that. So you have a rooted tree. You direct all the edges towards the root. Okay. So here is this example. So particles will enter at the leaves. Okay. Follow the same kind of dynamics. So whenever a particle enters, it finds the next available site along the unique path to the root. This is just a property of trees. So, and particles will exit at the root. Okay. So this is the root of the tree. Okay. So such trees are called arborescences for those who are interested. Okay, so now we have entrance rates. So leaf rates alpha L for L a leaf, and we have bulk rates beta I for each site I in the tree. Okay, so a particle which is here will hop with rate beta 1, particle will enter with rate alpha 1 over here, alpha 2, alpha 3, alpha 7, and alpha 9, and so on. Yeah, so this is the same kind of dynamics. So for this, many of the results go through, but now there are interacting currents. So that's what I want to mention. So okay, so now again, just like I had parameters lambda i's for the one-dimensional model. So the one-dimensional model is a special case which is just a path, right? So all this story generalizes in the following way. So let kappa I be the parameters for the leaf rates. Kappa L, let's say, and lambda I for bulk rate, leaf hops, let's say, and this for bulk hops, right? So I should say that the generator of this also has very explicit description for its eigenvalues in a similar vein as what we had. Yeah, so that's what allows us to solve this is there's a unique path. There's a unique outward path. There are many incoming paths, but there's a unique outgoing path. So the eigenvalues of the generator are explicit, and here, so the again now mu n can calculate for kappa L for L a leaf and lambda I. So this depends on so many parameters, and this is, as you might guess, this is given by the sum over leaves alpha L exponential of kappa L plus sigma I belongs to the path from L to R is the root of lambda I minus 1. Okay, so it's kind of the same story as we had for a single path. So each of these paths kind of sort of work independently in a sense, and that gives you this generating function, and the large deviation function joint large deviation function is again given in the same way. So f of JL for so f of all the j's is given by this, again the sum over leaves, again same kind of formula, JL log JL by alpha L minus JL plus alpha. Okay. And again, there's a story with the quasi-stationary distribution. One can calculate, the quasi-stationary distribution is the same, except that the currents for all the leaves will be modified. There'll be an alpha prime L for each leaf, and which will change the current. So in particular, so of course, product measure is the stationary measure also for this process, which I should have said. And so here you can do things like you can see correlations. Well, there aren't any, but in steady state. But you can try to see correlations across currents for different branches. So this is like, this is a fairly simplistic model from the physics point of view, because things are not really interacting, right? Because when a particle wants to hop, it'll just, overtake everybody, it'll just hop over everybody that is already there. So somehow the physics in steady state is quite clear, but I think it would be, as I said earlier, so this is kind of easy stuff. But it would be interesting to see how things approach equilibrium, approach the steady state in such models. So there's one nice property that it has, is that if you forget about the tree, if you go back to the original model, that the system of size n embeds in a very natural way in the system of size n plus 1. I mean this in an algebraic sense. There's an intertwiner, and that allows us to do lots of calculations out of steady state. So we have partial results, so if you're interested, I can tell you about this offline. Okay, thank you. Yeah.
So first going like
Yes.
3 was just a line. To get a certain J0,
Yeah.
you have to find out what should be the lambda 0, lambda 1, etc. across the
Yes.
various parameters. So there is a unique way to find out all these n parameters.
No, sorry, what do you mean?
So I want to see what is the limit law says that the current should be alpha naught, but I want something which is different.
Yeah.
You're saying that the most likely deviation is that all the currents are the same and they are all equal to J naught.
Right.
to capture this J0,
Yes.
I need those parameters, lambda 0, lambda 1. Of course, it's the f of J0 is the largest eigenvalue of that matrix. But how do I find
No, f is not. Mu is the eigenvalue, largest eigenvalue of that matrix.
So yes, that's correct. And then it's Fj is the Legendre transform of that.
Exactly.
But how do I find the from the Fj I want to compute the matrix that's likely to give rise to this deviation? So the typical.
Oh, right. So I didn't write the formula for the dupe transform. I can write it. Let me write it over here. So if you remember my notation, Mn was the generator of the original process, Ln was for the tilted generator, and M prime n is the generator for the quasi-stationary process. So M prime n of W prime W is given by Ln of W prime W times little ln of W prime by little ln of W minus the delta function W prime W times mu n, where ln this is the vector W in 0, 1 to the n is the left eigenvector, is the opposite one. Of ln with eigenvalue mu n. So all these have nice properties. I mean, they can be given very explicitly. I can write down the formula if you like. So from there you have this guy. Yes. Yes. Yeah.
Can you clarify what you mean by taking this to our equilibrium?
I mean, I just meant that since we know, I mean, let's in this case, we're looking at all these currents across bonds J0, J1, etc. We know that they converge in the long time limit, they will all be equal. It's natural to ask how this goes to 0. I mean, it probably grows exponentially, but with what rate and so on. So one can hopefully compute this very explicitly in this model. And that was the idea.
Okay. Let's thank Arvind.